Okay, and with that, we will start our first hands-on session. This hands-on session is session number 3, hands-on session number 3. We will talk about match action tables and how to use exact matching longest prefix match. So this session will be conducted by Elie, but you have access, all of you have access to the pod. So feel free to log in into the platform, and if you want to follow with Elie, you are welcome to do so. So Elie, do you want to start? And just to clarify, which lab is this in the lab set?
So this is gonna be lab number 6, which is called Introduction to Match Action Tables, Part 2. And we decided Part 2 because it contains some part from Part 1, and I think it's gonna be more comprehensive. So yeah, that's the lab. All right. So in this hands-on session, we will start by describing what are those match action tables, why do we need them when we deal with P4, and then we're going to see how we can implement them on BMV2 and test whether they are working or not. So in this slide here, we can see back the architecture that we discussed last time, and this is related to the V1 model. But basically, any architecture that is related to programmable data plane use as main component the match action tables. And those match action tables are defined within the programmable match action pipelines. So in the ingress and the egress, this is where we're going to implement the tables, the actions, and we will start by invoking those tables or applying those tables. Now, in a table, we can actually implement any kind of logic. So we can use it to implement some traditional switch tables for routing or flow lookup, ACL purposes. Or what is more important, especially for P4, is the ability to do customized user-defined complex logic, right? So in the previous presentation, we were seeing some very nice applications. Many of those applications are leveraging tables and these match action units inside the switch so that they perform their goal. So how does a match action table operate? We can see here we have in the match action table, we have a key, we have an action ID and action data. And basically, by default, those tables are empty, and we need to populate them with some entries, right? And usually, this is the job of the control plane to populate them. Okay, and then what we need to do is we need to get some fields from the headers and the metadata to construct a key. And this key will be used for lookup in our table. Now, once we have, we can have here two kind of scenarios. The key is there in the table, so we will have a hit. And if it's not there, we're going to have a miss. So if we have a hit, then the action that is in that specific record will be executed, and the action data will be passed to that as well, right? And you can see here, we have some action and it has a code, and we will be able to know whether we have hit or not, and therefore we can know what to execute in that action. So we know the action ID, so the name of that action, and the parameters of that action. Now, in case we have a miss, so the key is not found in our table, then we're going to be using the default action. And the table, when you define the table in a P4 program, you can specify what the default action is. And like in any other action, there's some action data that you can also pass to it. Okay, I can give here a very simple example. If you want to achieve Ipv4 forwarding, there's plenty of ways you can do that. This is completely decided by you as the programmer. But if you want to walk through this kind of example, in the match action table, let's say we called it Ipv4 forwarding table. We use the control plane to populate it with some entries. For example, here the key is destination IP, so 192.168.0.1. And then for the actions, we have one action which is called IP forward. And the action data would be what egress port on the switch to use whenever we have a hit on that destination IP. And then the key that we want to construct, we will extract it from the packet headers, destination IP. So after we do the parsing for, let's say, Ipv4, there we can now extract this destination IP. And we do a matching. We can see here that we have an entry, so we have a hit. And therefore, the IP forward action will be executed, and the action data eg_port = 4 will be passed to it as well. Now, what is this action doing? This is also defined by you as a programmer. In our case here, we are doing something like just setting the egress port of the traffic manager. So we are telling the switch where to forward this packet from. And we are here also decrementing the time to live. But again, this is not the only way to do it. So you can decide what to do there. And in this lab that we're going to go over now, we have this topology. So there's one P4 switch, a BMV2 switch, and 3 hosts, H1, H2, and H3. We will be implementing 2 tables. One table will use the longest prefix match, or LPM. And in this kind of matching, we basically match, as an example, we can match on a whole network rather than on just a single IP address. But it can be used for other matching besides matching on IPs. And then the other table would be to use the exact matching. So we will try to match on exactly the IP address rather than a whole network. And once we have a match, we will assign the output port. And then we will also update the MAC addresses in the headers and decrement the TTL. All right. So now I will go to the platform where we start doing the hands-on. So we are still using the same platform as we did last time. All you have to do is log in using your credentials. And once you are there, you have to just select lab number 6. So it's lab 6, introduction to match action tables, part 2. All right. So now we are inside the pod. We can see here we have one client, and the manual is located here in the content. So we can just display it. What I usually do, I undock this, put it aside. So I will put this on the left-hand side, and then the platform on the right-hand side. Okay. And so like the other labs, we will start first with some generic information about the lab. What is the objective, an overview about the topic discussed. There's a table for the credentials that the devices that you have in your topology might use. So for example, here, the password is password all small caps. You will see that we will use that while we are doing the lab. And then we will start by describing what is the objective of this lab, some little theory about what to expect in the hands-on later on. For example, here we are talking about the LPM, the longest prefix matching, and we are showing how a typical code looks like. But I will skip those and just go over the hands-on because we will be describing them as we type the code. So starting from section 2, this is where the hands-on starts. We will be using Mininet for emulating this whole network, and the switch that we will use is a BMV2 switch. So I will first click on my client here to enter to the VM, and then I will start Mini-Edit, which is the graphical topology editor for Mininet, and it's asking me for a password. The password is password all small caps. And now we are inside Mini-Edit. So we already built this topology so that we don't have to rebuild everything here for every lab. And you can find the topology file by clicking all file open and then specifying the lab number. In our case, we are doing lab 6. And then we select lab6.mn. So now that we have loaded the topology, the next step is to start the emulation, and we do so by clicking on the Run button. And now that those buttons are great, so it means that our topology has started and we are ready to go inside the host, perform any kind of command there, as well as on the switches terminal. So now we will see how we can get into one of the hosts. So for example, if I want to go to the terminal of host H1, all I have to do is right click on H1 and hold the right click. And then I will have to click on terminal. And here it's showing me the terminal of host H1. So I can issue here any command that you usually use on Linux. For example, ifconfig. So I'm here in step 2. I want to see the interfaces that I have on host H1. And we can see we have one interface, H1-ETH0. This is the IP address 10.0.0.1/8. And we have a loopback interface. All right. So now in section number 3, we'll start by defining the table in our P4 program. Before we do so, we first have to start our environment, and we will go to the terminal icon, which is on the desktop. And from there, we will type in code P4 labs, and then lab 6. This is to start the Visual Studio Code and use the lab 6 as the main folder. And what you can see here is, as we did last time, so we have different files for each part of the pipeline. So we have the main file is basic. So this is where we are invoking the switch instance. And then we have a parser. You can see it's already implemented. And we have the ingress block, egress, we have the parser, checksum, and so on. And as we were talking, whenever we implement those tables, we can implement them in the those ingress processing block or egress processing block. For now, we're just going to be using the ingress. And now I click on ingress.p4 to see the content of this file. We can see that we have a control called myIngress, and we have all the right parameters there, but it's still empty. So nothing has been implemented yet. And this is what we're going to start by doing now. So we're going to implement these tables that perform forwarding, right? But before we implement the tables, we have to list and define what are the actions that will be used by those tables. So for instance, I will start with one action, which is called forward, right? And to do so, you have to type in action and then the action name. So here you can call it whatever you want. We are just calling it forward. And then you can pass on parameters to this function. So these to this action. So these are the action data that we were discussing in the slides. What we are doing here, we are passing the destination MAC and the output port. Okay, now those types here are defined in the headers, and we discussed them last time. So this is how you can have type def and create your own type, right? But you can always say bit 48 instead of MAC address underscore T. So MAC address underscore T, DST address. Then we have egress spec underscore T port. And now we start by defining what is this action doing. So it's very similar to how we define a regular function. And so what is happening here is that we are setting the output port, which is part of the standard metadata. And metadata, if you recall, these are just the, this is some data that passes through the pipeline. And we have some standard metadata that contains some predefined fields that you would use for processing the packet. For example, if you want to set the output port, there is a predefined field called egress spec, right? And so what we are doing here, we are setting this predefined output port, which is part of the standard metadata, to be equal to port, which is whatever was sent from the control plane, right? This is the parameter here. So standard metadata dot egress underscore spec is equal to port. So again, I'm just passing, I'm just assigning the output port based on the value of this parameter, which we usually populate from the data, from the control plane, sorry. Next, we are doing here some a swapping for the MAC addresses. So what we are saying is we want to modify the source address inside the Ethernet header. So here we are doing header modification to be equal to whatever destination address was already in the headers. So I'm assigning the previous destination address as a new source address in the headers. And this is showing you here how Ipv4 can be used to apply packet header modification. In this case, we are changing the value of the source address to be equal to the previous destination address that was inside the headers. And if you want to change, for example, part of the IPv4, all you have to do is write hdr.ipv4. Whatever field that you are planning to modify. Okay, so hdr.ethernet.source address is equal to hdr.ethernet.destination address. And I just wanna say that those fields here that we are typing them, this is what we did last time, right? So you can see all of those in the headers, right? This is where I'm getting those names here. And if you define this as, let's say, dst_addr, then you have to use that later on in your table definition. Okay. And now we are assigning also the parameter from the control plane, passed from the control plane, which is the destination address or the MAC, to be equal to the new destination address. So hdr ethernet.dst address equal to st address. And also what we are doing here, we are decrementing the time to live. You can see here, so this is just an example to show you that you can use some basic expressions in Ipv4. For example, you are subtracting here 1. So hdr.ipv4.ttl is equal to the previous value of the ttl minus 1. And basically, that's it for the action. So now we just created an action called forward that accepts the destination MAC and the output port as parameters, and we'll do some processing. In our case, we are changing the output port of the traffic manager, and we are changing some fields inside the headers. Next, we will define another action, which is called drop. And the idea here is just to drop the packet, right? Whenever this action is being invoked. So I will also type in action. We will call it drop. So this is what we define it, right? The name of the action drop. You can obviously change the name to whatever you want. Now here, there is a predefined in the V1 model, something called mark to drop. And basically, it accepts the standard metadata here as parameters. And what it does is really is that it's just setting the output port to be the dropping port. Okay. But so far we defined those two actions, the forward and the drop, but we didn't create the table yet, or we didn't say that these two actions belong to a table. And basically, this is what we have to do next. So now we will create a table, which we will call IPv4 exact, because in this table, we will be using exact matching. So table, and then you give it a certain name, whatever you want to call it. Here we are calling it IPv4_exact. Now, in the table, we have to define what is the key, right, for that table. So what are we trying to match on? So we type in key equals to, and here we start by listing the fields that we want to match on. So for example, what we are doing here, we are saying we want to match on the destination address, which is part of the IPv4 header. And we want this match to be exact. So this is what we mean by exact matching. It means that we're gonna try to match exactly the same value as whatever is inside the header. We are not doing an LPM where we can try to match an IP from a certain network. So now we defined what is the key for this table. Next, we have to list what are the actions associated with this table. So actions, and we're gonna list the two actions that we created, right? So we have forward and we have drop. These are the two actions that we will use in our IPv4 exact table. We can also specify what is the size of this table. So how many entries do we want to store in that table? And obviously here you can't like select any number, you can make it very large. It depends on how much resources you have when we talk about real hardware. For here in this example, we are just using 1024. And we will specify a default action. So again, the default action will be invoked whenever there is a miss. So we don't find this key inside our table. So our default action here would be to drop the packet. So invoking the action drop. Okay. So this is what we have to do when we create a table. We have to create the actions that you are planning to use in the table. You have to specify the key, the lookup key. You have to specify what are the actions associated for that table, the size, and what is the default action in case you have a miss, or in other words, in case your key was not found in the table. Now, what we're going to do is we're going to create another table, and this table will be doing longest prefix matching instead of exact matching. So now I'm in step number 5 here, and basically we are calling this table IPv4 underscore LPM. So table IPv4 underscore LPM. And then the key is also the destination address from the IPv4 header. So HDR IPv4.dst address. But now instead of using exact for the match type, we're gonna use longest prefix match or LPM. Regarding the actions, we are gonna be using the same actions that we used for the previous table. These are forward and drop. Okay. Now, obviously, you can create other actions and have some actions for one table, other actions for a different table. But here, because both of these tables have the same purpose, which is forwarding based on the destination address, we just use the same actions in both tables. Okay. Now, same thing for the size. So size is 1024, and the default action is drop. Okay. Now, after creating the tables and listing all the actions that are associated with these tables, if you just keep it like that, nothing will happen. And the reason is every one of those control block, right? For example, my ingress, it needs to have the apply in it, this apply block. And basically what you can think of it as this block will start executing with whatever is inside the apply, and everything else before was just definitions, so they are not executed yet. So we have to write here apply. Now I'm in step 6, and basically here is where you can start by deciding what is the logic, which table you apply. If you want to have some if statements, you want to do some complex code later on, this is where you would actually do it, right? And so what we are doing here is we are creating an if statement, a condition just to check if the IPv4 header is valid. And by IPv4 is valid, here we mean, did we parse IPv4 when the packet was received? If the parser actually parsed IPv4, then there's an implicit flag bit that is set to valid. And therefore, this condition here will evaluate to true. Now, let's say you received an IPv6 packet, then your parser didn't parse the IPv4, and therefore this condition here will evaluate to false. Okay? So if header dot IPv4 dot is valid, so now at this point we know that our IPv4 was parsed, so we have an IPv4 header. We can start by applying the tables that we defined. So what we're gonna do is we're gonna say something like, let us start first with the exact matching table. If it is applied, then fine, it's enough. If not, then we will apply the LPM table, the longest prefix match. And to do so, we can also type here another condition. So if IPv4 underscore exact, so that's the table name, I'm applying it now, so dot apply, and then dot miss. So I'm checking here if we applied this table and we have a miss, so that there's no entry inside that table for this specific destination address. What we can do is we can now try to apply the other table, the IPv4 LPM. Okay, and it's really important to understand that when you look at some Ingress block, let's say you are trying to read some other code, it's always a good idea to start reading from the apply. So this is where you know the sequence of how those tables are invoked or any kind of processing that you do inside the data plane. So at this point, we know that we are checking for the validity of IPv4, and we are, if it is valid, we are applying the exact. If we have a miss, then we go to the LPM and apply it. Okay. And of course, at the end, we want to make sure to save. So just by using Control S or file save. And this is important. Otherwise, when you compile, you got to be using the empty version of this control block. So now step number 4, we will compile. This should compile successfully if we don't have like a typo. So p4c.basic, remember that we compiled the main file here that is calling the pipeline. And so it compiled successfully. There is no error that's being returned. And we have a basic.json file generated, which we will be using to actually define what is the data plane is. So this is the binary that you would usually use on a hardware. This is the output of the compilation. And therefore, because this is the output of our compiler, we need to push it to our switch S1. So now push to switch. We're going to specify the file to push. In our case, this is basic.json, and then the switch name, which is S1. Here we are asked for a password, and the password is again password all small caps. Next, we will verify that the file is in our switch. So we will go back to mini edit. And then we will go inside the terminal of the P4 switch to see if the file is there in the file system. So right click now on the S1 terminal. And there I will issue an ls command. And we can see we have our basic.json. It was pushed. So this is the one that we just compiled now, the output of our compiler. And then we want to make sure to understand what are the ports being used by the switch, so that whenever we start the daemon, we tell it that use this port as port 0, this port as port 1, and so on. So before we do that, we can see the interfaces that are available on our switch, ifconfig. And what we can see is we have basically the loopback. There is one interface for, this is for management, so we're going to skip that. But most importantly, we have S1 ETH0, S1 ETH1, and S1 ETH2. And basically, those are the interfaces that are connected to the host H1, H2, and H3. So these are the interfaces that you see here. Next, we will start the switch daemon. And we do so by using the simple switch command, which we see here. So simple switch -I. So port 0 on our switch will correspond to interface S1-ETH0. And then again, -I, port 1 is for S1-ETH1. Then -I2 for S1-ETH2. And we also supply here the nanolog parameter just to be able to see the logs inside the switch. And this file here is like, we just specified it. You can specify any other file basically for IPC. Now, most importantly, when you start the switch, you have to give it the output of your compiler. This is your definition of the data plane, which is the JSON file, right? And this is basic.json. And we also started in the background because we're going to do some more commands in the same terminal. It's telling us that it added successfully the interfaces and assigned them to those port numbers that we specified when we started the switch. Next, I will press enter here to return to the CLI. And then I will use this command here to populate the tables that we just created. So simple switch CLI. And we have a file that contains the rules or those table entries. We already created those. It's inside this folder, lab6, and it's called rules.cmd. And basically, I'm just getting it as input to this command here, simple switch CLI, which will insert those entries in the data plane. And now that we know a little bit about tables, we can see what is happening here. First, we can see that an entry was added to an LPM match table, which is called myingress.ipv4 LPM. And notice how it's using the control block first and the name of that table. So it's saying that we have a table ipv4_LPM, which is inside the block myingress. The match key for this specific entry is first, it's of type LPM and is A000/8. This means that if you change from hex to decimal, this is 10.0.0.0/8, which corresponds really to the network here on the left-hand side. And our action, so whenever we have a match here, we will execute the action, which is myingress.forward, and the runtime data. So remember, we had two parameters in the action. We had the destination MAC and we have the output port. And this is what we are seeing here. So this is destination MAC and this is the output port. Okay. And this entry that was added has a handle 0. So later on, we will see that when you navigate this tool, you'll be able to delete a certain entry by its handle and so on. Now we have another entry also for the same table, but this time the match key is 14, and this corresponds to 20.0.0/8. This is the IP address. And it has some also other action data, right? So this is the MAC and this is the output port. Now for the third entry, you can see here, we are now adding one to the exact table, which is myingress.ipv4_exact. And here the match key is also exact and 1E, which is 30.0.0.1. And notice here how we are using exactly the IP address rather than using a whole network as we did in the previous two entries. And whenever we have a match, we call the forward action and we pass with these two parameters. Okay, now in the second part, now the next session, we're gonna navigate this CLI so that we can see how we do all this table population manually. Basically what we are doing here, but we're gonna see how we can do it from scratch. Okay. Here, when you go through the lab, there's some explanation. Then we will start this nano message client just to be able to see the logs inside the switch. And now on host H2, we will start Python script that will sniff on a certain interface, H2 underscore ETH0. So to do so, we have to go to the mininet, right click on H2 and then terminal. And from there, just run this Python script here. Then we will go back to the terminal of host H1 and send the Ipv4 packet here to 20.00.1. So I have already host H1 terminal opened. I will just maximize it. And then type in send.py to the destination IP 20.0.0.1. Hello world. And basically here we can see that this is how the packet looks like. These are the headers. So we have Ethernet. On top of that, we have IP and we have TCP. And now we can see the logs of the switch to make sure that our tables were really used, right? So I will go to the behavioral model. This is the terminal for the switch. We start here by looking at the packet in. So a packet was received on port 0. The parser was executed, and we can see that we parsed Ethernet and IPv4, and then the parser ended here. So we parsed the IPv4. Next, we start with the ingress block. So this is pipeline start ingress. And here we see that there is a condition evaluation, and it's telling us that it evaluated true. And if we go back to the code, we are talking about this condition here, which is whether IPv4 is valid or not. In our case, because we parsed IPv4, then this validity bit was set to 1, and therefore our IPv4 is valid. Okay. And then we have a table being executed, which is IPv4 exact, but we have a miss. We don't have an entry for that. And this is because we didn't inserted this entry in our exact table. And so the default action would be executed, which is drop. However, whenever we have a miss, if we go to the logic here, when we have a miss, we will start by executing now or applying the LPM table, right? And this is what we are seeing here. So next we have the IPv4 LPM table, but now we have a hit, and that's because we inserted this entry from the control plane.
Elie, can I interrupt you, because there is a question that is exactly about this.
Sure.
The question is, if there is a miss with the LPM table as well, would there be an implicit drop?
It's basically what you write in the default action, right? You can have it as a drop so that you drop it. I believe if you don't write anything, like if you just keep it without this default action, then nothing will happen. So I think it might be an implicit drop, but I'm not sure. We can check that really.
Now in your code, line number 39 is clear. Default action is drop. So there is a drop. That's what you are referring to. There is going to be a drop.
Exactly. Yeah.
Thank you.
Sure. So now, so again, we were talking about this LPM table. We have a hit, and therefore there's an action that was executed. So the action that we executed was my ingress.forward. And this is basically this action here, right? And we executed this action, the pipeline is done. Next, remember in the architecture, we have an ingress and an egress pipeline. So we start with the egress, but the egress is empty. And you can confirm here that we have nothing in our egress, right? And then after that, we have the deparser, the checksum update, and we have the deparser to emit the table. And we can see at the end that the packet was transmitted out of port number 1. Okay. So imagine like you have a more complex application that involves other kind of header modification. All you have to do is define those actions, decide what you want to do there, and then create the tables. And you have to make sure to populate the tables from the control plane, and you will be able to have this custom packet processing. Now, I want to mention that what you write here inside the action, when we deal with software switches such as BMV2, it's very flexible because we don't have the limitations of the hardware. But when you start developing applications for the hardware, here you might have some limitations, specifically if you have a lot of data dependencies. So you have to wait for the output of one instruction to use it as input for the second, and so on. And you'll be limited by how many stages you have in your certain hardware switch. Okay, and that's where all the innovation comes in. You have to try to fit this program, which is not like a super easy task to do. It requires a lot of understanding of the hardware to be able to do it. For the software switch, we don't have this issue, so you can keep writing here, and it's gonna compile without any problems. So next here we are sending another packet, but this time for 30.0.0.1. This is also from host H1. So use the up arrow and then use 30 here. And if we go back now to the logs of the switch, basically we have to look at where the packet in is. So this is where actually this packet started at this point. Again, we have the parser executing at parsing IPv4. And then we have the condition, this condition evaluated to true, but now we have a hit on the IPv4 exact, right? And we have a hit, so we execute the forward action, and that's it. So we don't go for the LPM. If we had a miss like we had in the previous tab, then we go to the LPM table. And basically that's it for this labs. If there's any question, Dr. Jorge, I can take them.
Elie, thank you very much. There is a question in the chat window. So the action execute drop, the action drop after the first match table is not actually executed?
Yeah, that's a very good question. It is executed, but really this this action, when we talk about like this mark to drop, all this is doing is set the port to what they call the dropping port, right? But because later on we rechange this port to the actual egress port that we specify here, then you are overwriting it and it's not dropping the packet.
All right, thank you. Let's see if there's any other questions. There's no other question. Elie, briefly, do you want to just share with us your how important is this having the logs? Because you clearly follow the logs, and if you have the real hardware, you don't have this log. But fortunately, Intel has this Tofino model. So do you want to briefly describe your experience with the logs and how important it is?
Yeah, sure. So here at the University of South Carolina, we developed so far like a few Ipv4 applications. Initially, I started with BMV2, and then we went over the training and we went over the Tofino part. And when we developed those applications, like if you just try to implement it immediately on the hardware, it can be really, really tricky because there's a lot of things that you might think it's gonna work, especially if you are used to the regular programming, not the type of programming that you use for those ASICs. You might think it will work, but it actually doesn't. So you have to see the logs. For Tofino, there's the Tofino model. The nice thing about it is that it gives you more verbosity than even this BMV2 log, right? So there you can really see exactly what is happening. When you have, let's say, a hashing on some fields, you can see exactly what the hash value is. If you are using stateful elements, you can go really in detail and see exactly what is happening. So with the hardware, it's always a good idea. Start with the model, see the logs, make sure you are creating your program correctly, try to do a lot of testing. Typically, they use unit testing and the packet test framework, PTF, for more verification of the program. And then once you are sure, okay, it works well, all you have to do is just get the output of your compiler and then deploy it on the hardware. And basically, this is what we are doing with the pod that Dr. Jorge was showing. We just test on the model, we get the output, we deploy it there, and we run. So we don't even have to recompile on the hardware. It's exactly the same code. And then you'll be able to see in high performance whatever your results are.
Thank you, Elie. There is another question. How many match action steps does this example use?
So it depends on how many tables you are using. And there are some other elements that might use match action as well. But for now, we have 2 tables. So we are using the Ipv4 and exact and the Ipv4 LPM. And we try to do 2 matches here, one on the exact destination address and one on the LPM for destination address. And I think this is a good question when you deal with the hardware a lot, because there's a lot of what they call those action units and packet header vector, hash units. There's a lot of hardware ALUs. You will be able in the hardware to see exactly which one of those are being activated, are being used. Now for the model, it doesn't make a lot of sense to use or to get them. It's nice to know them because you know how complex your program is. But typically, this is like the kind of question that you go and see what the hardware is doing. And with that, we know with Intel, because we work with those switches. With the compiler, once you compile, it will produce some graphs and logs. And you go there and you inspect them, and it will tell you exactly how many hardware or how many units in this specific hardware you are using. So you know if you are consuming more stages, you know what is the SRAM and the TCAM and so on and so forth.
Right. So basically, that's something that BMB2 does not provide. But if you were really compiling with the P4 compiler for Intel, the compiler will be placing the tables in different stages and will show you how many stages you are using.
That's correct. Yeah, and they have like graphical interface, like a web-based interface, where you can see exactly the stages and how much you are consuming. So it's really nice because when you build complex and network applications, as Dr. Khe was saying, their compiler is smart so that it tries to place the tables correctly, right? But also it gives they give you the option to specify if you want to do everything manually and try to bypass those kind of things that are related to compiler optimization, right? But then it would require more understanding of the underlying hardware.
I don't see any other questions. So thank you, Elie. And we will continue with the last session of the workshop. We will have a break. Let's come back at 4 p.m. in 9 minutes, and we will have a hands-on session on populating this match action table from the control plane. That's what Elie will be doing in the next session. So we'll come back in 9 minutes. Right, we're back for the last session of this workshop. The hands-on session number 4 is about populating and managing match action tables at runtime. Elie will be leading this session. So Elie, I will let you share your screen.